Okay, so this is stoichiometry lecture part 2. The nice thing about this lecture is that there's no new concepts to understand. We've seen all of this before, and instead of using mass or grams, which we used yesterday, or today, whichever day, anyway, we're going to be using other units of measurement like volume, atoms, and molecules. All right, the process is still exactly the same. So just like we said in class today, the first thing that you have to do is find moles. Okay, regardless of what you have, the first thing you have to do is find moles. And there's only one exception to that, and that'll be in the last example today. All right, just as a reminder, 1 mole of any substance is equal to 6.02 times 10 to the 23rd representative particles, and 1 mole of a substance is equal to 22.4 liters of that substance as a gas, as long as it's at standard temperature and pressure. Just a reminder that standard temperature and pressure is 273.15 Kelvin and 101.3 kPa, which is the same thing as 1 atmosphere. So, let's take a look at example 1. Never mind, here's I was going to mess around.
Messing around.
Alright, so example number 1. This is the formation of phosphine gas from phosphorus and hydrogen gas.
I saw some Breaking Bad.
It's in Breaking Bad. Pretty cool. Does that have to be red phosphorus or white phosphorus?
Red.
Red phosphorus, not white. White's scary.
You get that from flares.
True story. All right, so example number 1. How many liters of phosphine gas, or pH3, are formed when 0.42 liters of hydrogen gas reacts with phosphorus? All right, so Mr. Herzog is writing down our given and unknown information right now.
Got it. All right, so we're going to start with our given unit, and we have 0.42 liters of hydrogen gas. And remember, the first thing you have to do is convert that to numbers of moles. So whenever you want to convert liters to moles, you have to use the relationship 22.4 liters is 1 mole of a gas at STP. And we're going to assume STP. Let's write that down.
Yeah, we didn't put that in there, but we'll pretty much always assume that STP. So
we have 1 mole of H2 occupies a space of 22.4 liters of H2. Notice how I am including all units and chemicals, so I know where I'm going.
So the liters of H2 cancels out. So now we've got our moles. So we go.
So whenever you have moles, you use the mole ratio.
Yep, that's right.
So if I have moles of H2 on top, I need to put moles of H2 on the bottom, and the unit I want to get to is moles of pH3. And I just pick the number in front to go with that chemical. So the 6 goes down below with the H2, the 4 goes on top with the pH3. And now my units cancel out. And now I don't want moles, I want liters. So I have to do the same thing again. So, or what I did over here. So to get from moles to liters, I'm going to put in 1 mole of pH3 that will occupy a space of 22.4 liters. And notice how the units do cancel out, and I'm left with liters of pH3, so I know I'm doing the problem right. And to do the work, I take 0.42 divided by 22.4 times 4 divided by 6 times 22.4, and I get an answer of 0.28 liters of pH3.
Woo woo.
Okay.
Let's look at example number 2.
Dose.
You want a different color?
Yeah, I picked blue. I'm not brown anymore.
Okay. All right, so example number 2. How many grams of nitrogen dioxide must react with water to produce 5.00 times 10 to the 22nd molecules of nitrogen monoxide?
Oh, man, you're forcing it this time.
I'm forcing it. Okay. So Mr. Herzog is once again going to write down our given and unknown information.
Molecules of nitrogen monoxide. Now, I can figure out which one of these is nitrogen monoxide. That's nitrogen dioxide. That's water. That's nitric acid. So this is 1O here. So that's the mono part of the monoxide.
Monoxide.
So this right here, there are 5.00 times 10 to the 22nd
molecules.
I can't spell molecules.
It's all right. They know what it is.
Molecules right here. And that's my given, and I want to know how many grams of nitrogen dioxide, which is this thing right here. So I want to know how many grams of this. So this is what my mole ratio is going to be between the nitrogen dioxide and nitrogen monoxide. All right, so we start with our given number, 5.00 times 10 to the 22nd. I'm going to put molecules below. Molecules of NO. And I got to multiply that by something to get it to go away. Now remember, 1 mole equals Avogadro's number, or 6.02 times 10 to the 23rd molecules equal 1 mole. So we have 1 mole on top, and 6.02 times 10 to the 23rd molecules of NO. We have NO up here. I understand this looks a little messy, but I just have to save. I don't have enough space. So the molecules cancel out. Now I'm left with moles of nitrogen monoxide. And I need to get to moles of nitrogen dioxide, so I use the mole ratio. So we know in 1 mole of nitrogen dioxide, there are 3 moles of nitrogen dioxide. And I use the mole ratio right here. And my units do cancel out, so moles of NO cancel out with moles of NO. And I have to convert moles to grams, so I have to find the molar mass of this right here. So oxygen, each oxygen is 16, so 16 plus 16 is 32, plus 14 is 46. So that's where the 46.0 grams of NO2 for every 1 mole of NO2. And if you did this correctly, your units do cancel out and you're left with grams. So you can multiply across the whole top and divide by on the bottom, or you just take 5 times 10 to the 22nd divided by 6.02 times 10 to the 23rd times 3 times 46.0, and you should get an answer. Oh, that's not a good line. You should get an answer of about 11.5 grams of NO2. Okay.
Okay, so as you can see, we're doing this pretty much the same exact thing that we did when converting from mass to mass, except we're using different units of measurement. So nothing has really changed. We just need to remember back from chapter 10 when we talked about all the things that 1 mole was equal to, whether it's Avogadro's number, the molar mass, or the molar volume.
Yeah, and again, it's just a big canceling game. Just make sure your units are canceling out, and that's how you know you're doing this correctly.
All right, so let's do one more example. And I kind of amped it up a little bit here. I know.
Ay caramba.
Ay caramba. All right, so in this case, we want to know how many molecules of water will produce 0.0325 kilograms of nitric acid. So, we're going to get our given and unknown information.
0.0325 kilograms.
Kilograms. So that's something we haven't seen before.
Dealt with kilograms yet.
Nope, we haven't dealt with kilograms yet. But we've dealt with something very similar to kilograms, and that is the
grams.
The gram. Okay, so the first thing we're going to have to do here is we're going to have to convert that kilograms to grams. And this was the exception that I was talking about in the beginning of this lecture. Okay, yeah, so we're going to take the 0.0325.
What did I started too far.
0.0325 kilograms. Okay, we're going to convert that to grams right off the bat. Okay, so I know that I said the first thing you have to do is convert to moles, but there are some special cases. Okay, so
kilograms is here, so we're going to put 1 kilogram at the bottom.
Kilogram on the bottom. Nitric acid.
And our 1,000 grams.
Mm-hmm. Okay, so we've converted here to grams, and that's going to end up being... Why don't we just write it out?
Just write out the number?
Yeah. I think that's...
So, 1, 2, 3.
All right, so 32.5 grams. Okay, so now we've gotten to a nice starting...
What the heck is that?
Yeah, what the... was that?
Oops.
Use the buzzer, Herzog. If you're going to cuss. Seriously.
That's not a bad word.
You can't say that word on... this.
I don't care.
Okay. So, we're going to that's going to become our new starting point. So now that we have grams, the first thing we're going to do is convert it to what, Mr. Herzog?
Moles?
Moles. We got to have moles. Okay, so once we have grams, we can find the number of moles. So we'll do the molar mass here of nitric acid, which is
Should be 63.
63.
48 plus 14, 62 plus 1, 63.
63.
So for every 1
Mole.
mole of HNO3,
NO3.
63.0 grams.
All right, so there's our molar mass of nitric acid, and our grams are going to cancel out.
Cancel.
All right, and so once we have moles, we can use our mole ratio.
Ratio. So if there's nothing here, that means it's a 1. So we have 1 to 2 ratio for every. There's 1 water for every 2 nitric acid. So I just have to pick which one goes on top. And since I have moles of nitric acid on top, that means I'm going to put the 2 moles of. That's not right. Oops. HNO3 on the bottom for every 1 mole of water on top, and my units should cancel out. And let's see, now I'm in units of moles of water. I don't want moles of water, I want molecules of water. So we need to do one more conversion factor. I'm running out of room, so I'm just going to keep on going down here. So we're going to multiply that by, let's see, if we say for every 1 mole of water, there are 6.02 times 10 to the 23rd molecules of water. And when you do this, moles will cancel out with moles. Okay, so this looks like a little bit of a mess, but we'll get through it. Let's be brown. So you take 32.5 divided by 63 divided by 2, and since this number is on top, you're going to multiply it by 6.02 times 10 to the 23rd, and let me just check my work real quick. And the answer we get, I'm running out of room, I'm going to put it right
down at the bottom.
I'll put it right here.
Okay,
The answer is 1.55, because we need 3 sig figs, and my number started with 3, times 10 to the 23rd molecules of water. And that's my answer.
Cool.
This writing is horrible.
That's all right. They can read it. All right, so endeth the stoichiometry lesson part 2. Remember, if you have any questions, let us know during class, and hope you enjoyed.
Bye.
Adios.